Okay, so you've sent in just a ton of stuff about number systems,
Yeah.
like notes and articles and, I mean, really the whole work. So it seems
Uh-huh.
like you're really interested in more than just what the different taxic numbers are.
Right.
You want to see, like, how they fit together,
Yeah.
like the big picture of numbers.
Exactly.
And maybe even have a few of those aha moments
Love
along the
to.
way.
Yeah.
Well, in this deep dive, that's exactly what we're going to try to do.
I like that.
We're going to map out the whole landscape of
I
numbers,
like that analogy.
starting with the ones we all know,
Okay.
the counting numbers.
Right.
And then we're going to expand our view to include a whole universe of numbers,
Okay.
each with its own unique properties.
Right.
And we'll see how they all connect.
Yeah.
And ultimately, by the end of this, you're going to have a really solid understanding of the real number system.
That's the goal.
All right, so to start,
Okay.
let's think about those counting numbers.
All right.
Like 1, 2, 3, 4, and so on.
Uh-huh.
Those are called the natural numbers.
Makes sense.
And then we'll add 0 to the mix
Okay.
to get the whole numbers.
So 0, 1, 2, 3.
Exactly.
All right.
And then we'll bring in the negatives
Okay.
to get the integers.
So like -3, -2, -1, 0, 1, 2, 3.
That's it.
Okay.
And then things get really interesting
Oh.
because we're going to talk about rational numbers,
All right.
which are numbers that can be written as a fraction.
Like frac dollars.
Exactly.
Like-
Not equal to 0, of course.
Yeah. So all of $2 where dollars and $2 are integers.
Yes.
And $Q is not 0.
Important point.
And we'll really dig into what defines rational numbers.
Okay.
And all the different ways they can be represented.
Okay.
But then there's a real turning point
Oh,
because we have to introduce irrational numbers.
okay.
These are the numbers that cannot be written as a fraction.
Whoa.
They're kind of the rebels of the number world.
I like it.
And there's a whole dramatic story about them, really.
Involving the ancient Greek mathematicians.
Oh, the Pythagoreans.
Exactly.
Cool.
And in the end, we're going to see how all of these numbers,
Uh-huh.
the rationals and the irrationals,
Yes.
come together to form the complete set of real numbers.
Okay.
And one really cool thing
Yeah.
is that there are infinitely many rational numbers.
Right.
But there are also infinitely many irrational numbers.
Wow. So 2 infinities.
Right. And it's kind of mind-blowing to think about how they all fit on the number line.
Yeah, that is mind-blowing.
But before we get too deep into the infinite,
Okay.
let's start by really understanding what makes a number rational.
Makes sense.
So as you've seen, a number is rational
Yeah.
if it can be written as frac at all,
Right.
where talo and talo are integers,
Uh-huh.
and q is not equal to 0.
Yeah, you keep saying that.
It seems important.
It is super important.
Why is that?
Well, it has to do with how our whole number system works.
Okay.
Division by 0
Uh-huh.
is simply undefined.
Oh, okay.
It's like mathematically impossible.
Really?
Yeah. If we let $Q be 0,
Uh-huh.
then the expression frac would just be meaningless.
Hmm.
It would be like asking,
Yeah.
what happens if you tried to divide a pizza into 0 slices?
I guess everyone gets 0 pizza.
It just doesn't make sense.
You can't divide something into 0 groups.
Exactly.
So that's why $Q can't be 0.
It's a fundamental rule.
Okay.
And it makes sure that every rational number
Uh-huh.
has a clear and definite value.
Makes sense.
Now, what's really neat
Yeah.
is that all those number systems we learned about early on,
Wow.
natural numbers, whole numbers, and integers,
Right.
they all fit inside the category of rational number.
They're all rational.
Yeah.
So can you give me an example?
Sure. Like, let's take the integer -25.
Okay. -25.
We can easily write that as a fraction.
How?
Just put it over 1.
So frac dollars, and that's a rational number.
Yes, because -25 and 1 are both integers,
Uh-huh.
and 1 is not 0.
Right.
So it fits the definition perfectly.
So all the integers are
Yeah.
actually rational numbers.
They are.
They're like a subset.
Right. It's like a smaller group within a larger group.
Okay, and what about whole numbers?
Well, they're integers too.
Right.
So they're also rational.
Even 0.
Even 0, because 0 can be written as frac
Oh,
dollar.
yeah, yeah.
And of course, the natural numbers are also integers.
Like 1 is just frac.
Exactly. So they're all rational.
Yep, all rational.
Okay, so we've got all these different fractions
Right.
representing rational numbers.
Yeah.
But when we put a rational number on the number line,
Uh-huh.
it occupies just one specific point.
Right.
It's like all those fractions are just different names for the same location.
Exactly.
Or like different addresses for the same house.
Perfect analogy.
So even though there are infinitely many fractions,
Wow.
each rational number has just one spot on the number line.
Right, and that brings us to the idea of equivalent rational numbers. Okay.
Different fractions can represent the same rational number.
Right, like frac and dollars.
Exactly. They're the same number.
They are. And we have a special way of writing rational numbers on the number line.
How?
We use the simplest form,
Okay.
which means the numerator and denominator have no common factors other than 1.
No common factors.
We call them coprime.
Oh, okay, coprime.
And that gives us a unique way to represent each rational number.
I see.
So instead of writing fracmacata on the number line,
Uh-huh.
we would write simplest form.
Right.
Okay, so now for a mind-blowing question.
Hit me with it.
Imagine you pick any two rational numbers.
Okay.
How many other rational numbers do you think you can find between them?
Well, I don't know, maybe a handful,
Maybe.
but I have a feeling you're going to tell me it's more than that.
It's way more than that.
Really?
It's actually infinitely many.
No way.
Yes.
Whoa.
So let's say our two rational numbers are 1 and 2.
Okay, 1 and 2.
We can find a rational number right in the middle
Okay.
by calculating their average.
So that would be frac 1 plus $2.
Uh-huh.
Which
Extra
is
frac $1.
3/2.
Right.
And now the crazy part is that you can repeat this process.
What do you mean?
You can find a rational number between 1 and 3/2,
Okay.
and another one between 3/2 and 2,
And so on.
and so on forever.
So there are infinitely many rational numbers between any two rational numbers.
That's exactly what it means.
That is mind-blowing.
It's like no matter how close together two rational numbers are,
Uh-huh.
you can always squeeze in infinitely many more.
Wow, so the rationals are really dense?
Super dense. It's like they're all crammed together on the number line.
Like a number party on the number line.
And there's always room for more.
Always room for more.
So with all these rational numbers packed in,
Yeah.
you might think that there's no space left for any other kind of number.
Right, if they're so dense.
But there
What?
are still gaps on the number line. You're kidding.
And those gaps are filled by the irrational numbers.
So even though the rationals are infinitely dense,
Uh-huh.
there's still room for other numbers.
That's the amazing thing about infinity.
Okay, so tell me more about these irrational numbers.
Well, they're kind of the opposite of rational numbers.
Okay, so they can't be written as fractions.
Exactly.
Hmm.
And the discovery of these irrational numbers
Uh-huh.
caused quite a stir back in ancient Greece.
Really?
Yeah, you see the Pythagoreans?
Those guys again?
They were a group of mathematicians who believed that all numbers could be expressed as ratios.
So they thought everything was rational.
Exactly.
What happened?
Well, one of their own members, a guy named Hippicus,
Okay.
figured out that there were some numbers that couldn't be written as fractions.
Like what?
Like the square root of 2.
Father?
Right, and legend has it
Oh, no.
that Hippicus was punished
For discovering a number.
for revealing this secret.
Seriously.
Because it challenged their whole worldview.
That's harsh.
Yeah, they believed that the universe was built on irrational numbers. And this discovery kind of shattered that belief.
Wow, so irrational numbers were like a forbidden secret?
Pretty much.
Okay, so officially, how do we define an irrational number?
Well, it's kind of defined by what it's not.
Okay.
And irrational numbers
Sure.
cannot be written as frac dollars,
Uh-huh.
where dollars and Q dollars are integers, and Q dollar is not 0.
So it's the opposite of the definition of a rational number.
Exactly.
I see.
And just like there are infinitely many rational numbers,
Uh-huh.
there are also infinitely many irrational numbers.
Wow, so two different infinities.
Right. And you gave some great examples earlier, like the square root of 2,
Okay.
the square root of 3,
Yeah.
the square root of 15,
I
pi, and that interesting decimal 0.101101111, and so on.
Oh, yeah, that one.
Where you just keep adding an extra one each time.
Right, it never repeats.
Exactly.
That's cool.
And it's important to remember
Okay.
that not all square roots are irrational.
Oh, right.
Like the square root of 4
Uh-huh.
is just 2.
Which is rational.
Exactly, because 2 can be written as frac.
So it's a fraction.
Yep.
Okay, so the square root symbol,
Yeah.
unless it's a perfect square inside,
Uh-huh.
usually means we're dealing with an irrational number.
Right, and we're always talking about the positive square root.
Okay, positive square root.
Now, your sources mention some other mathematicians
No.
who worked on irrational numbers.
Like who?
Like Theodorus of Cyrene.
Okay.
He proved that the square roots of a bunch of numbers, like
Uh-huh.
3, 5, 7, all the way up to 17,
Wow.
are irrational.
So he was busy.
And later on, Lambert and Legendre,
Those names sound familiar.
they proved that pi is irrational.
Pi is irrational.
Yeah, interesting.
And the proofs for why the square root of 2,
Uh-huh.
the square root of 3, and the square root of 5 are irrational
Okay.
are usually covered in more advanced math classes. I see.
But the basic idea
Yeah.
is that you assume the number is rational,
Okay.
and then you show that that assumption leads to a contradiction,
A contradiction.
like something impossible.
Oh, okay, so it can't be rational.
Exactly.
Okay.
So we've got these two groups of numbers.
The rationals and the irrationals.
Right. And when we put them all together,
What do we get?
we get the set of real numbers.
Real numbers.
Which is denoted by the letter R.
Capital R.
That's right.
Okay.
And every single real number
Uh-huh.
corresponds to a unique point on the number line.
So every point on the number line is a real number?
And every real number number is a point on the number line.
That's pretty profound.
It is, and it's thanks to the work of mathematicians like Cantor and Dedekind,
Oh, okay.
who really formalized this understanding of the real number line.
Cool.
So it's not just a bunch of dots representing fractions. It's a continuous spectrum filled with both rational and irrational numbers.
So how do we actually picture these irrational numbers on the number line?
Well, it can be tricky since they don't have finite decimal representations.
Right.
But your sources described some really cool geometric methods.
Oh, I like geometry.
Me too.
So what are these methods?
Well, let's start with the square root of 2.
Okay, imagine a square.
Okay, I'm picturing it.
With each side having a length of 1 unit.
1 unit square.
Right now, remember the Pythagorean theorem.
A squared plus b squared equals c squared.
Exactly.
That's for right triangles, right?
Yes, and it tells us that the diagonal of this square has a length of the square root of 2.
Because 1 squared plus 1 squared equals 2.
Right, and the square root of 2 is the length of the hypotenuse.
The diagonal of the square.
Exactly.
Okay.
So if we place one corner of this square at 0 on the number line, and we swing an arc with a compass, using the diagonal as the radius, the point where that arc intersects the number line.
Yeah, that's exactly where the square root of 2 is.
Whoa, that's really cool.
So we've actually pinpointed the location of this irrational number.
Just using geometry?
Exactly.
And can we do that for other square roots too?
You bet we can.
For me.
Let's find the square root of 3.
All right.
So we've got the square root of 2 marked on our number line.
Yeah.
Now imagine drawing a line segment straight up.
Up from the square root of 2.
Right, perpendicular to the number line.
Okay.
And make that line segment 1 unit long.
1 unit long.
Now draw a line from the origin
0
to the end of that 1 unit line segment.
Okay, I'm drawing it.
What shape did you just make?
A right triangle.
Right, and the length of the hypotenuse of that triangle is?
The square root of 3.
How'd you get that?
Well, the Pythagorean theorem again. The square root of 2 squared plus 1 squared equals 3.
And the square root of 3 is the length of the hypotenuse.
Right.
So if we swing an arc with a compass, using that hypotenuse as the radius, we can mark the square root of 3 on the number line.
Wow, so we've built a chain of square roots.
And we can keep going.
To find the square root of 4 and the square root of 5.
Exactly.
Yeah, that's amazing.
And your sources mention something called a square root spiral.
Oh, yeah? What's that?
It's a visual way to represent all these square roots.
Cool.
So you start with a line segment of length 1.
Okay.
Then you make a right triangle with that as one leg and another leg of length 1.
So the hypotenuse is the square root of 2.
Right.
Okay.
Then you use that square root of 2 segment as one leg of a new right triangle with the other leg being 1 unit long.
So the new hypotenuse is the square root of 3.
Exactly.
And we just keep going.
And the hypotenuses of all these triangles, they form a spiral.
A square root spiral.
And the lengths of those hypotenuses represent all the square roots.
Wow, that's beautiful.
So we can see how they all fit together on the number line.
Really cool.
Okay, so now that we've seen where irrational numbers live on the number line, let's talk about how we can recognize them just by looking at their decimal forms.
Okay.
Because rational and irrational numbers have very different decimal personalities.
Interesting.
So let's start by looking at the decimal expansions of some rational numbers.
Okay.
Like 10/3, 7/8, and 1/7.
All right.
If you do the long division for each of these, you'll notice some patterns in the remainders.
Okay.
For example, with 10/3, the remainder keeps being 1,
right,
which leads to the decimal 3.33 repeating forever.
With the bar over the 3?
Exactly. That bar means that the 3 repeats infinitely.
Okay.
And for 7/8, the division ends perfectly.
No remainder.
Right. So we get the terminating decimal 0.875.
Okay, so it's...
And for 1/7, you get a sequence of remainders.
Okay.
That repeats...
What's the sequence?
3, 2, 6, 4, 5, 1.
3, 6, 4, 5, 1.
And then it starts over again.
Oh, I see.
And that repetition in the remainders leads to a repeating block of digits in the decimal.
Which is?
0.142857 repeating.
Okay, so 14287, 142,857, and so on.
Exactly. And we use the bar notation again to show that that block of digits repeats forever.
Okay, so those are 3 examples of rational numbers. And their decimal expansions.
And your sources point out 3 key observations.
Oh, yeah, tell me.
First, when you do long division for any rational number, the remainders will either eventually become 0.
Like with 7/8?
Right.
Okay.
Or they'll start repeating a sequence.
Like with 10/3 and 1/7.
Exactly.
Okay, that's the first observation.
Second, the length of that repeating sequence of remainders will always be less than the divisor.
The divisor is the bottom number of the fraction, right?
Yes.
So like for 1/7, the repeating sequence has 6 digits. Which is less than 7.
Exactly. And third, when the remainders repeat, you get a repeating block of digits in the decimal.
Right, we saw that.
And this is true for all rational numbers.
So it's a universal property of rational numbers.
Exactly.
Right.
So the general rule is that any rational number will have a decimal expansion that either terminates or is non-terminating but repeats.
So it either stops or it goes on forever but with a repeating pattern.
Exactly.
Okay.
And the reverse is also true.
Meaning?
If you have a decimal expansion that either terminates or repeats, then that number is rational.
Okay, so like 0.5.
That terminates.
Right, it's just 1/2.
And 2.5.
That terminates too.
And we can write it as a fraction.
Okay.
Well, it's 2,556 10,000.
It's a frac.
Exactly. And that's definitely a rational number.
Right.
But what about those non-terminating, repeating decimals?
Yeah, can we convert those back into fractions too?
We can. It just takes a little bit of algebra.
Okay.
So let's take 0.3 repeating.
Okay, 0.3, 3, 4, and so on.
Right, okay.
Let's call that number
0.3 repeating.
And now if we multiply both sides of that equation by 10.
Okay. What do we get?
$10 equals 3.3 repeating.
Exactly. But we can also write 3.3 repeating as 3 plus 0.3 repeating.
Oh, right, because the 3's just keep going.
So we have $10 equals 3 plus dollars.
Okay.
Now we can solve for $1,000, subtract $1,000 from both sides.
So $4 equals 3.
And then divide both sides by 9.
So the first dollars equals 1/3.
And that's a fraction.
Wow. So 0.3 repeating is just 1/3?
Exactly.
That's neat.
And we can do the same thing for more complicated repeating decimal.
Can you show me?
Sure. Let's take 1.27 repeating.
Okay.
So let's set $14 equal to 1.2727 and so on.
All right.
Now multiply both sides by 100.
Why 100?
Because the repeating block has 2 digits.
Oh, okay.
So we get $120 equals 127.27 repeating, which we can write as 126 plus 1.27 repeating.
Right.
Or 126 plus dollars.
Okay.
Now we can solve for before.
Subtract from both
sides. 99 equals 126.
And then divide both sides by 99.
So having 26 over 99.
And that simplifies to 14/11ths.
So 1.27 repeating is just 14/11ths.
Exactly.
Cool.
And you can use similar techniques to convert any non-terminating repeating decimal into a fraction.
So every repeating decimal is rational.
That's the takeaway.
Okay, so what about irrational numbers then?
Well, if rational numbers have decimal expansions that either terminate or repeat, what do you think that tells us about the decimal expansions of irrational numbers?
Well, they can't terminate or repeat.
Why not? Because if they did, we could convert them into fractions.
Exactly.
And then they wouldn't be irrational.
Right.
So irrational numbers must have decimal expansions that are non-terminating and non-recurring.
You got it.
So they go on forever. And they never repeat.
Exactly. And remember that example we talked about earlier?
The 0.10111011?
Right. It's deliberately constructed so that it never repeats.
It's like it's running away from being random.
And then there are the famous irrational numbers.
Like pi.
On the square root of 2.
Their decimal expansions just keep going and going.
With no pattern.
And mathematicians have spent centuries trying to calculate more and more digits.
Wow. For example, your sources mention that the ancient Indian mathematicians in the Sulba Sutras had an incredibly accurate approximation for the square root of 2.
How accurate?
It matched the first 5 decimal places.
That's pretty impressive.
And the quest for the digits of pi has been a major endeavor.
Good imagine.
From Archimedes way back when to modern supercomputers that have calculated trillions of digits.
Trillion?
It's a never-ending pursuit.
So irrational numbers are full of surprises.
They are.
But how do we find irrational numbers between two rational numbers?
Ah, great question.
Because it seems like there's no space.
Well, there's always space with the irrationals.
Oh, right. They're dense, too.
So let's say we want to find an irrational number between 1/7 and 2/7.
Okay, 1/7 and 2/7.
We know they're decimal expansions.
Yeah.
1/7 is 0.142857 repeating. And 2/7 is 0.285714 repeating.
Okay.
So to find an irrational number between them, we just need to create a decimal.
Okay.
That starts somewhere between those two.
All right.
And then continues in a non-terminating, non-recurring way.
So it can't repeat.
Right. So we can start with 0.15.
Okay.
And then add some digits that make sure it never repeats.
Like what?
Like 0, 1, 5, 0, 1, 5, 0 is the 0, 0, 0, 1, 5, and so on.
Oh, I see the
You
pattern.
just keep adding an extra 0 each time.
So it never repeats.
Exactly.
And that's an irrational number.
Yes, and we could create infinitely many other irrational numbers.
Between 1/7 and 2/7?
Exactly.
Wow, that's crazy.
So even within that infinitely dense set of rational numbers, there's another infinite set of irrational numbers hiding.
It's like a number within a number.
It's like those Russian nesting dolls.
Okay.
Where you keep opening one.
There's another one inside.
And another one and another.
And they just keep going.
Okay, so now that we've explored the number line and all these different types of numbers, let's talk about what happens when we do math with them.
Like add, subtract, multiply, divide?
Exactly.
Okay.
We know that rational numbers are pretty well behaved.
What do you mean?
Well, if you add, subtract, multiply, or divide two rational numbers, the answer is always another rational number.
Oh, right. Like 1/2 plus 1/3 is 5/6.
Exactly. And we say that rational numbers are closed under those operations.
Closed meaning?
Meaning that if you start with two rational numbers and you do one of those operations, you always end up with another rational number.
You stay within the set of rational numbers.
Right. And rational numbers also follow those basic rules of arithmetic.
Like what?
Like the commutative law, which says that the order you add or multiply two numbers in doesn't matter.
Right, like 2 plus 3 is the same as 3 plus 2.
And 2 times 3 is the same as 3 times 2.
Okay.
And the associative law.
What's that one?
That one says that